I ended the last video asking you whether a certain sequence of vectors, namely the vectors 1, 2, 3, 4, 5, 6, and 7, 8, 9, were or were not linearly independent. And the answer is no, they're not linearly independent. So to see that, what you have to do is consider a linear combination A times 1, 2, 3 plus B times 4, 5, 6 plus C times 7, 8, 9 equal to the 0 vector, and find out whether there are any solutions to that where A, B, and C are not all 0. So if you write this out, you find that it's equivalent to a system of 3 linear equations, this system of linear equations. And even if this was a more complicated system of linear equations than that, you'd know how to solve those because you know about the row-reduced echelon form method. So one way or another we can solve those, and you find that actually there are infinitely many different solutions. In particular, there is a non-zero solution. For example, A equals 1, B equals minus 2, C equals 1 is a solution. Not all of the coefficients there are 0, and therefore the vectors are linearly dependent. They are not linearly independent. So now we're going to move on to the second in our key concepts about vectors and vector spaces, which is the concept of being a spanning sequence. To introduce that, I need the concept of the span of some vectors. So here's the definition. If you take vectors v1 up to vn in a vector space V, then the span of v1 up to vn, which we write like this, is the set of all linear combinations of v1 up to vn. In other words, it's the set consisting of all things of the form a1v1 plus a2v2 and so on up to an/vn, where the a's are scalars. So what that means is, if V was a real vector space, then the AIs would be any real numbers, and if V was a complex vector space, the AIs would be any complex numbers. So here we've used this notation, so the F refers to the real numbers if V is a real vector space, and the complex numbers if V was a complex vector space. So there's one not quite special case of this definition, but one case where it's important to be precise, and that's the span of the empty sequence. In some cases we'd like the span of the empty sequence to be defined, and so we define the span of the sequence with no elements in it to be the subspace of V consisting of just the 0 vector on its own. So that special case will actually come into play 1 or 2 times. Let's look at a couple of examples of spans. In fact, one example and one special case of the definition. So first of all, we'll have the vectors v1 is 1, 0, and vector v2 is 0, 1, which are elements, for now, we're thinking of them as elements of C squared. So what is the span of v1 and v2? Well, the span of vector v1 and vector v2, by definition, that's the set of all things x times v1 plus y times v2, where x and y here are complex numbers because we're thinking about a complex vector space. So that's the set of all things of the form x, y, just working out that vector addition and vector scalar multiplication, where x and y are complex numbers. Okay, that's all of C squared. Every element of C squared is in there. So we've shown that the span of v1 and v2 is equal to the whole of C squared. So one generic example, let's look at the example where you have the span of one vector. So the case n equals 1, whereby n I'm referring to the number here, and here, and here, and here, and here, and here. So what happens if n equals 1? Well, in this case we're taking a linear combination of just a single vector, but a linear combination of just a single vector is just a scalar multiple of that vector. So the span of a single vector v is just the set of all scalar multiples of that vector v. So the set of all AV where A is in F. And F here refers to the field over which the vector space which V belongs to is a vector space. So if V belonged to a real vector space, then F will be the real numbers, and if it belonged to a complex vector space, F will be the complex numbers. So that's what happens in the special case n equals 1. And if you think about some examples here where we have a geometric interpretation, like if this vector v was an element of r squared or r cubed, so two-dimensional space or three-dimensional space, then there will be a geometric interpretation of this span. The set of all scalar multiples of a vector, if that vector is not the zero vector, then it's the line through the origin and that vector. So this span in the case n equals 1, and when we're talking about two-dimensional space or three-dimensional space, this span would just be a line through the origin. So in that case, when we were thinking about the span of one vector, that span was actually a subspace. We looked at subspaces of r squared and r cubed, and we saw that amongst those subspaces there were lines through the origin. And in fact, it's always true that spans are subspaces, and that's what this proposition says. If you take any span of some vectors inside a vector space V, then it is a subspace of that vector space V. So to prove that, we'll introduce a bit of notation to save us from writing out span V1 up to Vn all the time. We'll just call that span S. And to prove that S is a subspace, we have to check the three subspace conditions. Number 1, containing the zero vector. Number 2, closure under addition. And number 3, closure under scalar multiplication. Let's do them one by one. So condition 1 is containing the zero vector. Well, the span is the set of all linear combinations of V1 up to Vn. So in particular, it contains the linear combination 0 times V1 plus 0 times V2 up to 0 times Vn. But 0 times V1 is always 0, 0 times V2 is always the zero vector, and so on. So this is just a bunch of copies of the zero vector, and when you add the zero vector to itself a bunch of times, you get the zero vector again. So this linear combination, which is an element of S, is the zero vector, and therefore the zero vector is in S. The next condition is closure under addition. So we have to take two arbitrary elements of S and prove their sum is again in S. So, well, what does an arbitrary element of S look like? It looks like a linear combination A1V1 plus A2V2 and so on. So we could write this in sigma notation as the sum from I equals 1 to n of AI Vi. And then we need another element of the span. So we could write that as the sum of Bi Vi, where these AIs and BIs are scalars. But if you add those things together, then the vector space axioms let you collect the coefficients of each AI and BI. So the associativity and commutativity laws and the distributivity laws in vector spaces allow you to gather the coefficients of each of V1 up to Vn. So you can rewrite their sum as the sum of AI plus BI times Vi. That is visibly a linear combination of the VI's. It's something times V1 plus something times V2 and so on. So as a linear combination of the VI's, it's an element of S. And that means we've proved that the sum of two elements of S is again in S. In other words, we've checked the closure under addition property for our set S. Finally, we have to show that S is closed under scalar multiplication. So we take an arbitrary element of S, which we can write like this, and we take an arbitrary scalar A. So A in F means A is an element of whichever of the real numbers or the complex numbers V is a vector space over. Then again we can use the vector space axioms to help us. If we look at A times our arbitrary element of S, well, we can move the A through the summation symbol by using the distributivity law in vector spaces a lot of times. And the vector space axioms allow us to rewrite this as the sum of A times AI times Vi. But again, this is visibly a linear combination of V1 up to Vn. It's something times V1 plus something times V2 up to something times Vn, which is a linear combination of the V's. So it belongs to S because S is the set of all linear combinations of the V's. We've shown that our scalar multiple of our element of S is again in S, and therefore S is closed under scalar multiplication. That means we've checked all three of the parts of the definition of being a subspace, and therefore the span is a subspace. Let's now look at an example span. So say we've got these two vectors here, and I should say where they belong to. These are supposed to be elements of R squared. And the question is, what is the span of UMV? So can we characterize this span in some nicer way, just other than just saying it's the set of all linear combinations of U and V? Well, we can. This span is all of R squared. So let's prove this. So we need to show, if we believe this statement, that every element of R squared is equal to a linear combination of UV. So let's take a typical element x, y in R squared. So I claim that there exist A, B, real numbers, scalars, such that A times U plus B times V is equal to vector xy. And that's what we need to do to prove that the span is all of R squared. We need to prove that every element of R squared is equal to something, a linear combination of U and V. So let's just rewrite this equation to see why this is true. What's this saying? This is saying A plus B, A minus B is equal to xy. So this equation holds if and only if A plus B, A minus B is equal to xy, and that holds, well, just extracting the two equations and solving them, that holds if and only if A is equal to x plus y over 2 and B is equal to x minus y over 2. So no matter what x and y were, this equation has a solution. We've shown that every element of R squared belongs to the span of U and V, but conversely the span of U and V is certainly a subset of R squared. It's just the set of all linear combinations of U and V, and those linear combinations certainly belong to R squared. So R squared is equal to the span of U and V. So let's move on and look at another example. We'll take U1 to be the vector 1, minus 1, 0, U2 to be 0, 1, minus 1, and U3 to be 1, 0, minus 1. So we might ask the question now, what is the span U1, U2, U3? Or, alternatively, we could just ask, is it all of R cubed? Let's be content with working that out. So is this span all of R cubed? So to solve this problem, let's rewrite it. So what we're asking here is it true that for any element x, y, z in R cubed, there exist A, B, and C in R such that AU1 plus BU2 plus CU3 equals X, Y, Z. Well, this is the kind of problem we know how to solve. This is a system of linear equations. We're asking, is it true that for any X, Y, and Z, the system of three linear equations, which arises from setting AU1 plus BU2 plus CU3 equal to X, Y, Z, has a solution? So we can solve these, for example, using row-reduced echelon form. Let's do it. So the equations we want to solve are, writing out AU1 plus BU2 plus CU3, we're trying to solve A plus C equals X, minus a plus b equals y, and minus b minus c is equal to z. Remember, we're trying to solve these for the variables a, b, and c, and we're trying to find out, is it true that for any x, any y, any z, there exists a solution? So we can solve these by using the method of row-reduced echelon form. So let's write down the augmented matrix. So we are talking about the three variables a, b, and c. And the coefficients are, as I've written down at the top there. So we have 1, 0, 1, minus 1, 1, 0, and 0, minus 1, minus 1. And the final column is the constant terms on the right-hand side of our linear equations, x, y, and z. The method of row-reduced echelon form tells you do row operations until you reach a matrix in row-reduced echelon form. So I've done this already, and I'll tell you what you get. You get 1, 0, 1, x, 0, 1, 1, x plus y, and 0, 0, 0, x plus y plus z. Okay, what does that mean about the solutions to those equations? So pause the video and think, what is this telling you about the existence of solutions to those equations? Okay, well, what I've got here is not quite in row-reduced echelon form, is it? It's taken us to this point, but to be in row-reduced echelon form, the leading entry on the last row must be 1. So if x plus y plus z is not 0, then the row-reduced echelon form matrix, which you can get by doing one further row op, is 1, 0, 1, x, 0, 0, 0, 1, 1, x plus y, 0, 0, 0, 1. This is a matrix which belongs to a system of linear equations with no solutions. There is a leading entry in the final column. So the final equation is 0 equals 1. There are no solutions to that equation. That means any vector x, y, z such that x plus y plus z is not 0 will not belong to the span. So you cannot solve the equations to show that x, y, z is in the span when the sum of x and y, z is not 0. In particular, for example, the vector 1, 0, 0 would not be in the span. So the span is for sure not all of R cubed. So we're finally ready to define a spanning sequence. Here's the definition. A sequence of elements in a vector space V is called a spanning sequence if the span of V1 up to Vn is all of the vector space V. And we've now seen several examples of these, so I'm just going to recap them. First of all, our very first example of a spanning sequence, actually we did c squared, but the same argument would tell you that 1, 0 and 0, 1 were a spanning sequence for R squared. And we also did some work to show that the sequence 1, 1, 1 minus 1 was a spanning sequence for R squared. We proved that the span of 1, 1 and 1 minus 1 was equal to R squared. On the other hand, on our previous slide, we proved that 1 minus 1, 0 0, 1, minus 1, and 1, 0, minus 1 is not a spanning sequence for R cubed. Now, if you're looking really carefully, you'll notice that these two are in the opposite. They're not in the same order that they were on the previous slide, but it doesn't make any difference. So if you reorder the elements in a sequence, you don't change what the span is, because linear combinations don't depend on the order of the things in that linear combination. Vector addition is always commutative and associative, so you can reorder as you like. So the arguments on the previous slide really do show that this thing is not a spanning sequence for R cubed, as, for example, whoops, wrong tool. As, for example, 1, 0, 0 is not in the span of these three vectors.